everyone. Hello, YouTube. So, welcome back to our CCNA, free CCNA for 2025. So, for today's topic, we're going to discuss about IPv4 header and why it's important to know this topic. So, before, we're only focusing about the source and the destination whenever we do routing. But why we need to study IPv4 is because we need to know how does a packet routed to our network. And take note, we're talking about packets, and if you still remember when we discussed the PDU, so packets is on the layer 3 of the layer 3 on our network. So we're not going to discuss the frames, the switching, or even the layer 4 or the application side. We're only going to focus on the packets itself. Okay, so I grab picture on the net on how does it look like. So this is all the details that a packet has. Okay, so whenever you transfer data from one device to another, it's not going to be only data, right? So it's impossible for you to send just the data itself. So you need to have the header for the router, for the network, to identify where to send it and how are we going to send it. And these are all the informations that we needed in order for us to transfer that packet, to route that packet. Okay, so again, this is the data part, so we're not going to discuss this one, but this is mainly the actual information that you need. So it could be the video, the image file, it could be certain information that you need to access on the internet. So this IP option, this is also optional. I don't think it will be needed on the CCNA. But right now, what we're going to focus would be this part of the packet, which is the IPv4, which is the v4 header. Okay, so IPv4 header, so it's 20 byte. So on this one, it consists of 4 byte for each row. So 4 byte, if you still remember, 1 byte means that's going to be 8-bit. Okay, so 8-bit. So if it's a 4 byte, so that's going to be 4 times 8, so that's going to be 8, 16, 24, 32. So it means that this packet, this would be a total of 32-bit. Okay, so let me just erase this one because I only have one pad. So if it's 32-bit, so we can illustrate here 1, 2, 3. Oh, sorry, we need to start from 0. So 0, 1, 2, 3, 4, so on and so on until we reach the number 31. Okay, so this is 4 byte, and the default size of a packet, like what I mentioned, it's going to be 20 bytes. So why 20 byte? Because we have 5 rows here. So 1, 2, 3, 4, 5. So it means 4 times 5, that's total of 20. So that's the size of IPv4 header. And we're going to discuss each of these fields in the IPv4. So the first part, though I don't have the size here, but the first part, this would be the version. So right now we're only using 2 versions, so IPv4, so it's either IPv4 or IPv6. So we do have IPv5, but it's not used. It's for I think it's a test, and it's not totally used for public. It's only used now for testing or some sort of like that. You can search about it, but right now we only have 2 types of packet, which version would be IPv4, which is what we're using right now, in IPv6, something that we also discussed on our previous lecture. So on the version, we're going to see here either version 4 or version 6. Now for the header link, so this will be the size of the header. So the default size of this one, so this is a 4 bit. So this is also 4, and total length would be 16. So in total, and this one type of service, that's going to be 8. Okay, so for this one we have 4, and then for the header length we also have 4. So the default size of this header length, it's going to be 5. So again, it's a 4-bit, so it means that the value of 5, if you remember, so it could be 1, 2, 4, 8. So it means that the maximum value of this header length would be 15, because if you add this one, 8 plus 4, 12, plus 2, 14, plus 1 would be 15. So the maximum possible size of a header or this IPv4 would be 15, but the default, like what I mentioned, the one that we've mentioned, it's going to be 20 bytes. So that's going to be 5, because it's going to be incremental of 4 incrementals. It means like 4 times 5. So the bit value of that would be like this: 0, 1, 0, 1. So this would be the value that you're going to see on the header link. And if you're going to, okay, let's just, I think it's best to show it using Wireshark. So let's try to analyze one packet here. So for you to see what does a header length means and what does 4-bit. If we're going to maximize the maximum header, that you're going to see the value of 1111 on our packet. But since we're only using the default most of the time, even if we're going to run a Wireshark, we can see that the default value of that would always be the 5, which is again incremental to 4. So that's why 5 times 4 would be the total size of a packet. So here, let's see. Let's just try to let's stop from here. So let's check. So we're only going to focus on IPv4, so we're not going to talk about the Ethernet frames and the IPv4 version. But if we're going to see the header length, this is version 4. So the header length would be 0101, like this one. So 0101. So again, 0101, that means the value of this would be 5. Now for the version, if you're going to see here, there's representation for IPv6. Not necessarily it's a bit, but it's just like the default that they're using. For IPv4, we're going to see the value of this. If it's IPv6, you're going to see it like that. Let's try to check if there's like an IPv6 running here. But this looks like an IPv6. Okay, so as you can see, 0101 for the version IPv6. Okay, so now let's move to the next field. So type of service, so this is an old one, but if you're going to see the latest RFC, we're not using TOS, but we're using DSCP for IPv4 header. So that's differentiated service. Well, let me see, differentiated service code point. So its purpose is the same. So this is where we apply QoS, or classification of traffic. So this is the part wherein we prioritize certain packets. So if you remember, we have like voice traffic, we have video streaming traffic. So there's a different label to those packets just for them to be prioritized on every streams of packets, or every time that we route packets. But again, this is old, but right now we have 6 bits for DSCP. You can look at the net, and the remaining 2 bits, that's going to be the ECN. Let me check if I still got it right. So this is an old one. Where's the new one? This one. So DSCP, and the 2 bits, that's ECN, this one. So DSCP and 2 bits, and again, those are for labeling or prioritizing traffic. So next would be the total length. So this will be 16 bits. So total length is different from header length. So for header length, it's only for the header itself. For the total length, it includes the segmentation, like different layers. So that's different from the size of the header length. So it's going to be 16 bit. So it means that if you're going to times the maximum value for this one would be 16 bit raised to power of 2 raised to power of 16. So the maximum value would be this. I hope you can see my screen. So that's the maximum value of packets, so 65,536. Okay, so that's for the first row. Now for the second, let me just erase all of this. Now for the second row, that's for the fragmentation. So for fragmentation, remember that there's a default MTU size for every device. Usually we set this on the actual interface itself. If you've noticed, there's like a configuration for MTU, or maximum transmission unit. The default value would be 1,500 byte. So every time that the packet exceeds 1,500, it needs to be fragmented. So the identification part, this is the label. We're going to see which packets belongs to each other. Okay, usually they do have the same identification for us to know, or for the device to know that this is just one chunk of information that was fragmented. Okay, and this is 16 bit. Remaining would be IP flag. It's going to be 3 bit, and this one would be another 13 bit. So for IP flag, we're going to see 0 is for, so it's a 3 bit, so 0 is for the reserve. The next one, it's either you know if it's fragmented or it should be fragmented or not. So let's check the IP flag. So either the second bit would say fragment me or not fragment me. I can't totally recall, but let's look it up on the net. So the IP flag value on IPv4. So I'm searching it through the net. So okay. Okay. Let's look at the meaning. Okay, the most important beats are don't fragment, and more fragments TF set. So this is this. Why we don't have exact information. Let me just look. Okay. Meaning na lang. Let's let me check. Why there's no IP flag value for IPv4 header? Okay, I think this is good. So the first one is reserve. The second one would be don't fragment, and the other one is more fragment. So it means that if we're going to see, where's my note? If we're going to see here, like 0, 1, 0, it means based on this documentation, don't fragment, it means that don't fragment. So it means that you don't have to fragment this one. This is a good packet on its own. If the value would be 011, it says here fragment, so it just mean that there would be fragmentation for this packet, and we can search that through here. Let's see for this one. So if you can see, so it says here 010. So 010, it means don't fragment. So if you see 011 here, it means that there's like a fragmentation happening. Okay, so that's the IP flag. And the fragment offset, the purpose of this is for us to know, or to the device to know, the position of packets once it's transmitted to the other end of devices. I mean, to the destination itself. So usually the positioning, the reconstruction of those packets will happen on the destination. Okay, so this one, this would identify the location of all those packets. So remember, whenever we transfer packets, it doesn't need to always to send it continuously or like in order. So it depends on the connection, it depends on the device, right? So sometimes it will not happen in sequence. So that's the reason why we have fragment offset, to identify what will be the position of those packets once it's already on the destination side. Okay, the third row for this one, I think this is the last part we're not familiar with, right? Because the fourth and fifth, we know it's a 32-bit because it's an IP address, right? So TTL, time to leave. So this is 8-bit in value. So 8-bit, so that's around 255. So it is a way to prevent loopings or infinite loop on the network. So I think the recommended value would be 64 hops before it disconnect the packet. You can actually see this whenever you ping a device or even a public website on the net. Protocol, this would be the actual protocol, like the TCP or UDP, and there's like a certain port designed for them, but it's not actually the port that we use to block them, but in the header they do have the same different value, like let's say IP header, IPv4 header protocol value. Okay, let's see. So it's an 8-bit field. So this one, so this is the value that you're going to see. If it's a TCP, it's going to be 16. If it's UDP, it's going to be 17. So as you can see here, it's 6. So it means that we're using TCP protocol for this packet. Okay, so that's the purpose of it. But again, that's a different from TCP port, because so that's it's not included on the IP header. Okay, header checksum. So this is where you're going to check the errors only in the header side, if there's like a problem or error checking, or do we need to resend it or not. And the fourth and fifth, to complete the IP header, would be the source address and the destination. Again, all of these are 32-bit, which is something that we're familiar with. So the 192.168, we all know that this is divided into 4 octets, and each octet consists of 8-bit. So that's why they are 32-bit in value. So that's the IPv4. Why it's important to know that, because on our previous topic in NAT, that's where the changes happen when we're going to translate a specific private IP to a public network. Okay, so that's all for our lecture today. Thank you so much for listening, and please, if you like the video, please like the video, share it, so that I can create more videos for you guys. Thank you, and goodbye.